Tonight, we are going somewhere very far away. Not just far in the way that a long drive feels far, or far in the way that a cross-country flight stretches the hours. We are going to the edge of our solar system, to a world so distant that the sunlight reaching it is nearly 1,000 times dimmer than what touches your window in the morning. We are going to Neptune. And if you have never spent much time thinking about Neptune, that is perfectly all right. Most people haven't. It sits at the very back of the lineup, the last of the 8 planets, the one that tends to get skipped over in favor of Saturn's rings or Mars's rust-colored deserts or Jupiter's storm-wrapped bulk. Neptune is easy to overlook. It doesn't have the drama of a red spot. It doesn't have famous rings you can see with a backyard telescope. It doesn't have a moon people write songs about. But what Neptune does have quietly, at the cold and remote edge of everything familiar, is something genuinely worth knowing about. It has winds that move faster than anything ever recorded on any other planet. It has storms that appear and disappear without explanation. It has a magnetic field that behaves in ways that still puzzle scientists, and an interior so extreme and so strange that it may be producing something that sounds more like a fairy tale than a fact of physics rain made of diamonds, falling gently through crushing darkness toward a solid core we have never seen. Tonight, we are going to spend some time with Neptune. We are going to descend through it, layer by layer, and let ourselves sit with how quietly astonishing it is. There is no rush. The universe is patient, and so are we. So settle in, get comfortable, let your shoulders drop a little, and let's begin. There is something worth pausing on before we go any further, which is simply how little we actually know about Neptune, and why that is. We live in an era where we have sent rovers to Mars that can drive themselves around craters and drill into rocks and take selfies. We have orbiters around Jupiter that have mapped its moons in extraordinary detail. We have a spacecraft called New Horizons that travelled all the way to Pluto and then kept going, deeper into the outer solar system, sending back data even now. The point is, we are quite good at exploring things. When we decide something is worth visiting, we generally find a way. And yet, Neptune, the 8th planet, one of only 8 worlds in our solar system, has been visited exactly once. A single spacecraft, a single flyby, and that encounter lasted less than a single day. Voyager 2 arrived at Neptune on August 25, 1989. It had been travelling for 12 years since its launch, crossing the vast emptiness between the planets in a long curving arc that had already taken it past Jupiter, Saturn, and Uranus. By the time it reached Neptune, the people who had sent it on its way were older. Some of them had moved on to other projects, other careers. And then, after all that waiting and all that distance, Voyager 2 spent just a handful of hours close enough to Neptune to gather meaningful data before sailing on into interstellar space, where it still travels today. What it saw in those hours, what it managed to transmit back across 4.5 billion kilometers of empty space, rewrote what scientists thought they understood about the outer solar system. And in some ways, the questions it raised are still waiting to be answered. No spacecraft has returned to Neptune since. No orbiter circles it. No probe has descended into its clouds. When we talk about what Neptune is like, nearly everything we know comes from that single day in 1989, supplemented by telescope observations from Earth and some clever theoretical modelling. In cosmic terms, Neptune remains almost entirely unknown. And yet what little we do know is, in its quiet way, one of the most remarkable collections of extremes in the solar system. Tonight we are going to go through all of it, slowly, carefully, one layer at a time. Let's begin where Voyager 2 began at the top of the atmosphere. From a distance, Neptune is beautiful. There is no other word for it. It glows a deep, rich bluish shade that feels almost deliberate, like someone chose it carefully. It is brighter and more vivid than Uranus, which tends toward a pale, washed-out blue-green. Neptune looks genuinely blue, in a way that feels almost warm, despite existing in a place where the temperature hovers around negative 200 degrees Celsius. The blue comes from methane. Specifically, it comes from the way methane in Neptune's upper atmosphere absorbs red light and reflects blue light back toward the observer. This is the same reason Uranus appears blue-green. Uranus also has methane in its atmosphere. But Neptune's blue is deeper, richer, and more vivid than Uranus's, which suggests there is something else at work, some other compound or property that enhances the color. Scientists have proposed various candidates over the years, but as of now, no one is entirely certain what gives Neptune its particular shade of blue. Even the color of the planet, at a basic level, is something we haven't fully explained. Beneath that beautiful blue surface, which is of course not a surface at all, but simply the top layer of cloud that we can see the atmosphere begins. Neptune's atmosphere is made mostly of hydrogen and helium, as you might expect from a giant planet. But unlike Jupiter and Saturn, which are predominantly those two gases all the way through and are classified as gas giants, Neptune and Uranus have a different composition deeper down one that earns them the label of ice giants. That name is a little misleading, because what it refers to is not exactly ice in the way we normally think of it, but we will get to that. At the top of the atmosphere, the temperatures are extraordinarily cold. Roughly negative 210 degrees Celsius near the cloud tops cold enough that the air itself would feel incomprehensible to any human sense of temperature. Cold enough that materials we think of as gases here on Earth would be frozen solid. And yet this is the warmest part of Neptune. Things get stranger and more extreme the deeper you go. What makes the upper atmosphere worth lingering on, though, is the wind. The wind on Neptune is the fastest ever measured on any planet in our solar system. At the cloud tops, winds have been recorded at speeds exceeding 2,000 kilometers per hour. 2,000. To put that in perspective, a Category 5 hurricane on Earth, the strongest category of storm, the kind that flattens cities, has sustained winds of roughly 250 kilometers per hour. Neptune's winds are roughly 8 times faster than that. The fastest winds ever recorded on Earth, in any context, barely exceed 400 kilometers per hour in an extreme tornado. Neptune's winds move at 5 times that speed, continuously across a planet so large that the entire Earth could fit inside it roughly 57 times over. And here is what makes those winds even more quietly remarkable. They are blowing in the wrong direction. On most planets, including Earth, the equatorial regions tend to experience winds that flow in the same direction as the planet's rotation. Neptune's equatorial winds, however, blow in the opposite direction, While the planet itself rotates in one direction, the winds near the equator push backward, against that rotation. This kind of flow pattern is called retrograde wind, and it is something scientists still do not fully understand. The planet is doing something to its own atmosphere that we cannot yet adequately explain with the models we have. The energy that drives those winds is another puzzle. Neptune receives very little sunlight, less than 1,000th of what Earth receives, given how far it is from the Sun. On planets like Jupiter, the wind patterns and storm systems are at least partially driven by solar heating. On Neptune, sunlight is so faint as to be almost negligible as an energy source. Something else must be powering those 2,000 km/h winds. And we will come back to that, because it connects to one of the deepest mysteries Neptune contains. Deeper into the atmosphere, beneath the cloud tops, we enter what scientists call the troposphere, the layer where weather happens. This is where Neptune's storms live. When Voyager 2 arrived in 1989, the most prominent feature it observed was a massive storm system in Neptune's southern hemisphere. Scientists named it the Great Dark Spot. It was roughly the size of Earth, a vast, swirling vortex of cloud and wind, an anticyclone spinning in the opposite direction from the storms around it, dark against the lighter blue of the surrounding clouds. It looked, in some ways, like a cooler cousin of Jupiter's Great Red Spot, the famous storm on Jupiter that has been raging continuously for somewhere between 300 and 500 years. Scientists who saw the Great Dark Spot in 1989 assumed it was similarly stable, similarly long-lived. But when the Hubble Space Telescope turned its attention to Neptune in 1994, the Great Dark Spot was gone, vanished completely. In its place were new cloud formations, new patterns, and eventually a new dark spot appeared in Neptune's northern hemisphere. That one has since disappeared too, replaced by yet more formations. Neptune's storms are not stable. They form. They grow to enormous size. And then, for reasons that remain genuinely unclear, they dissipate and vanish, leaving no obvious trace of what ended them. The dynamics that govern when a storm appears, how large it becomes, and what causes it to fall apart are not well understood. We know storms form, and we know they disappear. The mechanism connecting those two facts is still, in large part, a mystery. What we do know is that Neptune's storm systems move. They drift across the planet's face over the course of months or years, traveling from higher latitudes toward the equator. As they move, they seem to weaken, and near the equatorial region, they tend to break apart entirely. Why the equatorial zone of Neptune is inhospitable to large storm systems is another open question. There are also smaller, brighter cloud features on Neptune, thin, white streaks that form and disperse relatively quickly. These bright clouds are thought to form when strong updrafts push material from deeper in the atmosphere upward, where cooler temperatures cause it to condense into visible cloud. These features come and go on timescales of hours to days, and they trace the contours of the enormous wind currents flowing beneath them. The overall picture of Neptune's weather is one of extraordinary restless energy, storms appearing from nothing, winds screaming at speeds that make our most severe weather events look like a gentle breeze, and cloud patterns shifting and reorganizing constantly. All of this happening in a place receiving almost no energy from the sun. on a world no spacecraft has visited in over 3 decades. Now let us go deeper. Below the troposphere, below the visible weather, we descend into a region of the atmosphere that marks a kind of transition, a place where the nature of the material around us begins to change in fundamental ways. On Earth, if you descend into the ocean, the water is still recognizably water. It behaves the way water behaves. The pressure increases, the light fades, the temperature shifts, but the basic character of the material doesn't transform into something alien. On Neptune, going deeper means entering territory where the familiar rules begin to bend. As pressure increases with depth, the gases of the upper atmosphere become denser and denser, until they are no longer quite behaving like gases at all. The boundary between gas and liquid is not a sharp line the way it is on Earth. There is no surface to reach. No shoreline where the atmosphere ends and something solid begins. Instead, there is a gradual transition into an increasingly dense fluid state of matter that doesn't have a clean everyday equivalent. The deeper you go, the more exotic the chemistry becomes. Hydrogen, helium, methane, water, and ammonia are all present in various proportions. Under extreme pressure, these materials start to interact in ways that don't happen in everyday conditions. Methane, in particular, begins to behave very differently under the pressures found deep inside Neptune. At relatively modest pressures, methane is simply a gas, the same methane that makes up much of natural gas here on Earth. But under the extreme conditions of Neptune's interior, methane molecules can be broken apart, the carbon and hydrogen atoms separate. And the carbon under sufficient pressure and heat can recombine into a new structure. Diamond, the carbon atoms, stripped from their hydrogen partners and compressed under conditions of extreme pressure, can link together into the rigid, crystalline structure that defines diamond. And those diamonds formed in the darkness deep inside Neptune would not simply sit there. They would be subject to gravity, and so, slowly, they would fall. The image that forms from this is one of the most quietly astonishing things that planetary science has to offer. Inside Neptune, there may be a gentle, eternal rain of diamonds falling through darkness toward the planet's core, accumulating there over billions of years. This is not mere speculation. Experiments conducted here on Earth using powerful lasers to recreate the extreme pressures found inside ice giant planets have produced direct evidence that diamond formation can occur under these conditions. Research published by teams including those at the SLAC National Accelerator Laboratory has confirmed that when materials resembling Neptune's interior composition are subjected to the right pressures and temperatures, diamonds do indeed form. The physics supports it. The experimental evidence supports it. How large those diamonds grow, how quickly they fall, and whether they accumulate in a thick layer around the core or are dispersed in some other way, these are questions that remain open. But the basic phenomenon, the idea that Neptune may be a planet that rains diamonds through its interior, is something the evidence genuinely supports. Take a moment with that, if you like, somewhere out there at the edge of our solar system, in the cold and the dark, diamonds may be falling. Deeper still. As we descend further into Neptune's interior, we enter a region that scientists refer to as the mantle, though it is not a mantle in the way Earth has a mantle, which is solid rock. Neptune's mantle is something entirely different, something that for a long time had no good equivalent in human experience, and only recently has been studied closely enough to begin to understand. The material in this region is what gives Neptune and Uranus the classification of ice giants. But again, the word ice here does not mean what it usually means. It refers to a class of volatile compounds, mainly water, ammonia, and methane that are present in large quantities and that, under ordinary conditions, would be solid ice or liquid. Under the conditions deep inside Neptune, however, they are neither quite ice, nor quite liquid, nor quite gas. Water, in particular, does something remarkable under extreme pressure. Here on Earth, water is a familiar, well-behaved molecule. Two hydrogen atoms bonded to one oxygen atom. Liquid at room temperature, solid below zero, gas above 100 degrees Celsius. Water behaves the way water behaves, and we build our entire biology around that behavior. But under the pressures found deep inside Neptune, pressures millions of times greater than the atmospheric pressure at Earth's sea level, combined with temperatures of thousands of degrees Celsius, water does something that has no parallel in everyday experience. Its molecules don't fully break apart the way they would in a plasma. But the bonds holding the hydrogen atoms loosely in place do change. The oxygen atoms lock into a regular crystalline lattice, a structured arrangement, the way ice forms. But the hydrogen atoms, instead of moving with the molecules as a unit, become free to wander through that lattice. They move. They conduct electricity. This state of matter is called Superionic ice. It is simultaneously solid and liquid, in a sense crystalline in structure, but with freely moving charged particles. And because those charged particles can move, it is electrically conductive. It behaves in some ways more like a metal than like water. Research published as recently as January 2026 in the journal Nature Communications has continued to shed light on Superionic ice and its behavior under conditions matching what we expect inside ice giant planets like Neptune and Uranus. Scientists are increasingly confident that a significant portion of Neptune's interior may be in this state vast oceans of superionic water, pressing down from enormous depths, conducting electricity and playing a central role in generating the planet's magnetic field. This is the nature of Neptune's interior. Not a world of rock and iron wrapped in gas, not a ball of ordinary frozen water. Something in between, and something beyond a strange, dense, electrically active fluid that behaves unlike anything you would encounter anywhere on Earth. And now we arrive at the magnetic field. Because if any single aspect of Neptune captures how genuinely strange this planet is, it may be this. Every planet with a significant magnetic field, Earth, Jupiter, Saturn generates it through some version of the same basic mechanism. Electrically conductive material moves around inside the planet, and that moving charge generates a magnetic field. The field, broadly speaking, is aligned with the planet's rotation axis. It comes out near the North Pole, wraps around the planet, and goes back in near the South Pole. The geometry is not perfect, but it is roughly aligned with the axis. If you imagine a bar magnet sitting inside the planet, roughly along its spin axis, you have the basic picture. Neptune's magnetic field does not work this way. Neptune's magnetic field is tilted about 47 degrees away from the planet's rotation axis. This means the magnetic North Pole is not near the geographic North Pole. It is not even close. It sits at a dramatic angle to the direction the planet spins. That alone would make Neptune unusual. But there is more. The magnetic field is also offset. On most planets, the magnetic field is roughly centered on the planet's interior. The theoretical bar magnet sits near the middle. On Neptune, the center of the magnetic field is displaced significantly from the planet's geometric center. It is not centered on the core. It appears to be generated somewhere in the middle layers of the planet's interior, rather than deep within it. The combination of these two properties of field tilted nearly 50 degrees from the axis and offset from the center creates a magnetic environment at Neptune that is extraordinarily complex. As the planet rotates, the magnetic field wobbles and shifts relative to any point in space near the planet. The magnetosphere, the region of space influenced by the magnetic field, changes shape and orientation continuously. Scientists believe the magnetic field is generated primarily by the movement of superionic water and other electrically conductive materials in Neptune's middle interior, rather than deep in a metallic core the way Earth's field is generated. The irregular placement of those conducting layers may explain why the field is both tilted and offset. But the precise dynamics are still being worked out. Uranus, incidentally, has a similarly tilted and offset magnetic field. This is one of the reasons scientists are so interested in ice giants. As a category, these two planets seem to share a pattern of magnetic behavior that sets them apart from the other planets, and understanding why may reveal something fundamental about how magnetic fields can form in planetary interiors. For any hypothetical spacecraft trying to navigate near Neptune, or for any future probe trying to understand the planet's interior by measuring the magnetic environment, the field's complexity would make interpretation genuinely difficult. Neptune does not make things easy. It rarely does. Let us talk about Neptune's interior heat, because it is one of the things that most puzzles scientists about this planet. Neptune, despite being 4.5 billion kilometers from the Sun and receiving almost no solar energy, is not as cold as it should be. Or more precisely, it radiates more energy than it receives. When astronomers measure the heat output of a planet, they compare how much energy comes in from the Sun with how much energy the planet emits back into space. For most planets, these numbers are roughly in balance, or the planet's emissions can be accounted for by relatively simple processes. But Neptune emits approximately 2.6 times more energy than it receives from the Sun. The planet is producing significant heat on its own from within. This is not unheard of. Jupiter, for instance, radiates about twice as much energy as it receives. Likely as a result of slow gravitational compression, the planet is still very gradually contracting from the cloud of gas and dust it formed from, and that contraction releases energy. Saturn does something similar. These are old planets, but their interiors are still warm from the energy of their formation, slowly leaking out into space over billions of years. Neptune doing this is consistent with that pattern. The mystery is not that Neptune produces internal heat. The mystery is what happens when you compare it to Uranus. Uranus and Neptune are sometimes called twin planets, They are nearly the same size. Uranus is only slightly larger. They have similar compositions. They formed in similar parts of the solar system, presumably under similar conditions. Their magnetic fields share the same unusual tilted offset structure. In almost every way that planetary scientists use to classify worlds, these two are close cousins. But Uranus radiates almost no excess internal heat. It emits energy in rough balance with what it receives from the sun. Uranus's interior is cold, or at least appears to be. Whatever process is keeping Neptune warm does not seem to be at work inside Uranus, or if it is, something is trapping the heat and preventing it from escaping. Why are these two nearly identical planets so thermally different? This question has been a genuine puzzle for decades, and there is no consensus answer. Some scientists have proposed that Uranus experienced a large collision early in its history, a massive impact that could have disrupted its internal structure, altered its rotation axis, and perhaps created some kind of thermal barrier that prevents interior heat from reaching the surface. Uranus does spin on its side, with its axis tilted nearly 90 degrees relative to its orbital plane, a posture that is unusual enough that some kind of dramatic early event seems like a reasonable explanation. Others have proposed that Uranus and Neptune have different internal layering, and that the arrangement of material inside Uranus happens to trap heat more effectively. If denser material sits above lighter material in a way that inhibits convection, the process by which warm material rises and cool material sinks heat could accumulate inside without being able to escape. These are intriguing hypotheses. None of them has been confirmed. Without a dedicated mission to either planet, without an orbiter or probe that can map their interiors, sample their atmospheric compositions, and measure their heat flow directly, we are largely guessing. And so Neptune continues to glow, quietly and persistently, from the inside. Now let us spend some time with Neptune's moons. Because they are part of what makes this corner of the solar system so layered and interesting, and because one of them, in particular, is something genuinely worth knowing about. Neptune has 14 known moons. Most of them are small, irregular, dimly lit rocks that orbit at various distances. Some in the same direction as the planet rotates, some in the opposite direction. They are the kind of moons that planetary scientists note on charts and catalogue carefully, but that tend not to inspire a great deal of poetry. And then there is Triton. Triton is Neptune's largest moon, and it is one of the strangest moons in the solar system. It is about the size of our own moon, slightly smaller, in fact, and it is a cold, geologically active world of nitrogen ice and ancient craters. But the thing that makes Triton remarkable is its orbit. Triton orbits Neptune backward. Every other large moon in the solar system orbits its planet in the same direction the planet rotates. This is the natural outcome of how moons form. They coalesce from the same disk of material that formed the planet, and so they end up moving in the same direction. Triton does not. It orbits Neptune in the opposite direction to the planet's rotation, in what is called a retrograde orbit. This tells us something important. Triton was not born where it lives. It came from somewhere else. The most widely accepted explanation is that Triton originally orbited the Sun independently, as part of the Kuiper Belt, the vast ring of icy objects beyond Neptune's orbit that includes Pluto and many other small cold worlds. At some point, billions of years ago, Neptune's gravity captured Triton and pulled it into orbit. The process of capture would have been complex and energetic, likely involving interactions with other objects, and Triton would have had a highly elliptical, chaotic orbit for a long time after. Gradually, over billions of years, tidal interactions with Neptune would have circularized that orbit, made it smoother and more round, while also leaving Triton in its unusual retrograde path. The energy dissipated during that orbital circularization would have been enormous, likely generating enough heat to have kept Triton's interior warm and geologically active for a long time. Voyager 2 observed Triton up close, and what it found was fascinating. The surface is dominated by nitrogen ice, with vast plains of frozen material and a peculiar terrain that scientists describe as cantaloupe terrain, a lumpy, mounded landscape that looks somewhat like the skin of a cantaloupe melon. This pattern is thought to result from a process called diaporism, where slightly warmer material from below rises through the colder surface, pushing up and deforming it. Voyager 2 also captured something quite unexpected: active geysers on Triton's surface. Not geysers of hot water, as you might find in a volcanic context, but geysers of nitrogen gas. Dark material, possibly nitrogen mixed with organic compounds, shoots upward from the surface, carried by nitrogen gas that has been heated slightly by sunlight absorbed below the surface. These plumes rise several kilometers into Triton's thin nitrogen atmosphere before being caught by winds and drifting downwind in dark streaks across the ice. An icy moon, 4.5 billion kilometers from the Sun, with geysers. Neptune is the kind of place that rewards patient attention. There is, however, a melancholy note to Triton's story. Because Triton's orbit is retrograde, because it is traveling against the direction of Neptune's rotation, tidal forces are gradually slowing it down rather than speeding it up. Over time, this means Triton is very slowly spiraling inward toward Neptune. In roughly 3.5 billion years, Triton will come close enough to Neptune to be torn apart by tidal forces, and its material will likely spread out into a ring system that would dwarf anything Saturn currently has. 3.5 billion years is a very long time. Our Sun will be nearing the end of its life by then. But the universe keeps its appointments, and Triton is, in a very patient sense, falling toward its end. Neptune also has rings, faint, incomplete, and quite different from Saturn's brilliant bands, but rings nonetheless. The rings of Neptune were suspected before Voyager 2's visit, based on observations of how Neptune's silhouette affected the light of stars passing behind it. But the data was puzzling. The rings seemed to only partially encircle the planet. Some observations suggested arcs rather than complete rings, which was difficult to understand physically, because the dynamics of ring particles generally cause them to spread out into complete rings over time. Voyager 2 confirmed the rings and revealed why they seemed like arcs. The material in Neptune's rings is not evenly distributed. There are concentrations of denser, clumpier material at certain points along the ring sections that are noticeably brighter than the rest. Scientists call these concentrations ring arcs. The most prominent ones have names: libet, egalit, and fraternita nod, from the researchers who studied them to the French Revolutionary slogan. What keeps these clumps from spreading out? The leading explanation involves small moonlets that orbit within or near the rings, and whose gravity shepherds the ring material into concentrated regions. A moonlet called Galatea is thought to play a key role in maintaining some of the ring arcs. Its gravitational resonance with the ring material may act as a kind of orbital fence, keeping particles from dispersing too widely. This mechanism was not entirely well understood even at the time of Voyager 2, and without a return mission, our ability to observe whether the ring arcs are changing has been limited. Observations with the Hubble Space Telescope have suggested that at least some of the ring arcs may be fading or changing over time, which would mean the shepherding mechanism is not perfectly stable, and the rings of Neptune may be evolving on a timescale of centuries or millennia rather than the geological timescales of most planetary features. Neptune's rings are yet another feature of this planet that sits in a category of uncertain, partially understood phenomena observed, documented, theorized about, and not yet fully explained. Let us take a moment to consider where Neptune sits in the context of the broader solar system's history, because it has a larger story than simply being the eighth planet. The formation of the solar system was not a calm, orderly process. It was messy, violent, and chaotic by any reasonable standard, though the chaos unfolded over such long timescales that each individual event might have felt, from the outside, like a slow rearrangement rather than a catastrophe. The current leading model for how the outer solar system took its shape is called the Nice model, named after the city of Nice in southern France, where some of the key researchers were working when they developed it. The Nice model proposes that in the early solar system, the four giant planets, Jupiter, Saturn, Uranus, and Neptune did not form in their current positions. They were closer together, and closer to the Sun, in a more compact arrangement. Over time, as they interacted with the vast disk of icy debris that surrounded them, the material of what would eventually become the Kuiper Belt and Oort cloud, their orbits gradually shifted. Gravitational interactions with billions of small icy objects caused the planets to migrate. Jupiter moved slightly inward. Saturn, Uranus, and Neptune moved outward. At some point, Jupiter and Saturn reached a gravitational resonance configuration where they orbited in a simple ratio relative to each other, and this resonance disrupted the entire outer solar system. Neptune and Uranus were scattered outward. Vast quantities of icy debris were flung in every direction. Some of it fell into the inner solar system, contributing to what planetary scientists call the Late Heavy Bombardment, a period of intense asteroid and comet impacts on the Moon and the terrestrial planets that left the cratered landscape we still see on the lunar surface today. In this telling of the solar system's history, Neptune played a significant role. As it migrated outward, it ploughed through the Kuiper Belt, scattering objects and reshaping the outer solar system's architecture. Pluto and the other Kuiper Belt objects that cluster in orbital resonances with Neptune, the Plutinos, as they are called, were locked into those resonances by Neptune's passage and have remained there ever since, like footprints in the cosmic dust of a journey billions of years ago. The Neptune we see today, orbiting calmly at the edge of the solar system, is the aftermath of a period of dynamic upheaval that shaped everything from the moon's cratered face to the distribution of comets in the outer reaches of the sun's domain. We have not yet talked about what it would actually be like to visit Neptune, not just to observe it from a distance, but to send something into it to descend through those clouds and experience what the planet is, rather than simply what it looks like. This is something scientists have thought about carefully, because a probe dropped into Neptune's atmosphere similar in concept to the Galileo probe that entered Jupiter's atmosphere in 1995 is one of the things that would tell us the most about the planet. What elements are present in what ratios? How the temperature and pressure change with depth, what the clouds are made of, whether there are layers of distinct chemistry at different altitudes. A probe entering Neptune's atmosphere would begin at roughly the level of the visible cloud tops, where the temperature is around -200 degrees Celsius and the winds are immediately violent, remember, 2,000 kilometers per hour. The probe would need to be extraordinarily well built to survive the initial descent, decelerating from interplanetary velocity into the atmosphere at enormous speeds, experiencing intense heating from the friction of entry. Assuming it survived entry, and modern material science suggests it could, at least initially the probe would begin falling through the upper cloud layers. The first clouds it would encounter are thought to be primarily methane ice fine, crystalline particles suspended in the frigid air. Below that, depending on the composition models, there may be layers of ammonia and hydrogen sulfide clouds, similar to what Jupiter and Saturn are thought to have, though Neptune's specific layering is not well constrained by current observations. As the probe descends further, the pressure climbs. The temperature rises not toward warmth, but towards something less extreme than the frigid cloud tops, then beyond, into genuine heat as the compression of the atmosphere generates energy. By the time a probe reached a pressure of roughly 10 times Earth's atmospheric pressure, the temperature would already have climbed well above 0 degrees Celsius. The materials in the atmosphere would be increasingly dense and increasingly exotic. At some point, likely not long after reaching that 10-bar level, measured in minutes rather than hours, the probe would be crushed. The instruments would fail. The casing would deform. The data link to any orbiting relay spacecraft would go silent, as the probe was compressed into the dark interior of a planet that does not take visitors well. But those minutes of data, those few precious minutes of direct measurement from inside Neptune's atmosphere, would be worth more to planetary science than almost anything else we could do at Neptune short of a full orbiter mission. Knowing the precise chemical composition of the atmosphere, the temperature and pressure profiles, the presence or absence of particular compounds, these things would answer questions that have been open since 1989. So why hasn't it happened? Why hasn't a dedicated Neptune mission been sent? The honest answer is a combination of factors, and it is worth understanding them rather than simply lamenting the situation. The first factor is distance. Neptune is 4.5 billion kilometers from the Sun. Even traveling at the enormous speeds achieved by interplanetary spacecraft, tens of kilometers per second, the journey from Earth to Neptune takes roughly 12 years. That is 12 years of a mission where the spacecraft could fail, where a component could degrade, where the team of scientists and engineers who designed it could retire or move on. It is a long commitment, and space agencies have limited resources. The second factor is mission windows. The alignment of planets that allowed Voyager 2 to visit Jupiter, Saturn, Uranus, and Neptune in a single grand tour was a rare geometric opportunity. The planets happened to be arranged in a way that made a gravity-assisted multi-planet tour possible, and that alignment occurs only once roughly every 175 years. Sending a mission to Neptune on its own, without that assist, is much more difficult and requires more fuel, more time, or some combination of both. The third factor is competition. Every decade, the planetary science community engages in a process called the Decadal Survey, a prioritization exercise where scientists collectively rank the missions they most want funded. The most recent decadal survey, completed in 2022, did recommend a mission to the Uranus system as a high priority, an orbiter and probe that would study the ice giants up close. But the process from recommendation to funding to launch to arrival is measured in decades. Even if such a mission were approved and funded immediately, it would not reach Uranus for many years, and Neptune would be a separate and additional mission. The fourth factor is simply the nature of exploration. We have limited spacecraft, limited budgets, and an entire solar system worth of unanswered questions. Mars is a priority because of its potential relevance to life. Europa is a priority because of its subsurface ocean. The Sun itself is a subject of intense study. Every mission funded is a mission that competes with other worthy candidates, and Neptune, important as it is, has so far not reached the top of the queue. This is not a failure of ambition or curiosity. It is the reality of doing science with finite resources in an infinite universe. But it does mean that for the foreseeable future, what we know about Neptune comes largely from that single day in 1989, and from the patient work of astronomers studying it through telescopes on Earth and in orbit. There is something worth sitting with here as we move toward the deeper parts of our time together. Neptune is not just one planet at the edge of one solar system. It is a representative of a type of planet that appears to be extraordinarily common in the galaxy. When astronomers study the planets orbiting other stars, exoplanets, as they are called, they find that the most common planet types in the galaxy are not rocky worlds like Earth or gas giants like Jupiter. The most common types are planets intermediate in size, larger than Earth, but smaller than Neptune and Uranus, or roughly Neptune-sized themselves. These planets, which have no equivalent in our own solar system, are sometimes called super-Earths and mini-Neptunes, and they are everywhere. The galaxy appears to be filled with them. If we want to understand the most typical kind of planet in the Milky Way, if we want to understand what conditions are like on the most common worlds, and whether any of them might harbour life in some form, or liquid water, or conditions we might recognize, then understanding ice giants like Neptune is not an academic exercise. It is one of the most consequential things planetary science could do. Neptune sits at the edge of our solar system, overlooked and undervisited, and yet it may be the key to understanding billions of worlds across the galaxy. The physics operating inside it, the chemistry of its atmosphere, the dynamics of its magnetic field. These may be replicated in various forms on worlds orbiting other stars that we will never be able to visit in person, but will study from afar for centuries. Understanding Neptune is, in a quiet way, understanding the universe. Let us return for a moment to Voyager 2, because it deserves to be remembered properly. Voyager 2 launched on August 20th, 1977. It carried a golden record, a disk of sounds and images from Earth, a kind of message in a bottle addressed to anyone or anything that might find it in the distant future. Music from many cultures, greetings in many languages, the sounds of ocean waves and wind and thunder, a record of who we were, placed on a spacecraft and sent outward. Voyager 2 flew past Jupiter in 1979, past Saturn in 1981, past Uranus in 1986, and then on August 25th, 1989, past Neptune. That final encounter, Neptune, was the last time Voyager 2 came close to any planet. After Neptune, it continued outward into the vast emptiness that lies beyond the solar system. In 2018, Voyager 2 crossed the heliopause, the boundary where the sun's solar wind gives way to the interstellar medium, the thin, cold gas and dust that fills the space between star systems. It became only the second human-made object to reach interstellar space, following Voyager 1, which had crossed that boundary earlier. As of now, Voyager 2 is more than 19 billion kilometers from the Sun. It is still operational. It is still transmitting data. The signals it sends travel at the speed of light, and even at that speed, they take more than 17 hours to reach Earth. Scientists are still receiving information from an object that was launched nearly 50 years ago, that has traveled further than any human artifact in history, and that began its journey by sailing past the turbulent clouds of a gas giant and ended that planet-by-planet journey in the cold blue glow of Neptune. There is something deeply moving about that, in a quiet way. Voyager 2 spent less than a day at Neptune, the last planet it would ever visit, and then kept going. It left behind a world full of unanswered questions and carried with it the sounds of Earth into the darkness between stars. Neptune will still be there when we return. The storms will have come and gone. The diamonds will still be falling, perhaps. The Superionic water will still be pressing and conducting in the dark. Triton will be slightly closer to its eventual dissolution. The magnetic field will still be wobbling in its strange, offset, tilted dance. Neptune is patient in its way. It has been waiting 4.5 billion years. It will wait a little longer. Let us think about what a future mission to Neptune might look like. Because scientists have thought about this, and the plans that have been sketched out are worth knowing about. A dedicated Neptune orbiter, a spacecraft that would enter orbit around Neptune and study it continuously over several years, rather than simply flying past, has been discussed and proposed many times. The scientific case for it is compelling. An orbiter could map the planet's magnetic field in detail, tracking how it changes over time and how it interacts with the solar wind and with Triton's thin atmosphere. It could study Neptune's cloud systems continuously through multiple seasons, watching storms form and dissolve and understanding, at last, what governs their appearance and disappearance. It could observe all 14 known moons from close range, studying their surfaces, their orbits, and their interactions with the planet's magnetic environment. And it could gather data on Neptune's rings, confirming whether the ring arcs are fading and whether the shepherding moons that maintain them are behaving as the models predict. There is a useful comparison to reach for here. When the Cassini spacecraft entered orbit around Saturn in 2004, it began a mission that lasted 13 years. In that time, it made hundreds of close passes of Saturn's moons, dipped repeatedly through the ring plane, sampled the composition of the rings directly, and delivered a probe called Huygens into the thick atmosphere of Titan, Saturn's largest moon. Huygens descended for more than 2 hours through Titan's orange haze and transmitted data all the way to the surface, revealing lakes of liquid methane, dunes of organic material, and a world of genuinely astonishing complexity that no one had fully anticipated. Cassini transformed what we know about Saturn in ways that would have been impossible from a flyby. Scientists cite it regularly as a model for what a similarly committed, long-duration mission at Neptune could achieve. The questions waiting at Neptune are, if anything, more numerous and more fundamental than the ones Cassini set out to answer at Saturn. The science case is not in doubt. The technical challenges, however, are real and worth understanding clearly. The first challenge is simply getting there. Neptune is not on the way to anything. It sits at the very far edge of the solar system's planetary neighborhood, and reaching it efficiently requires either a very long transit time traveling in a straight-ish line, or a carefully choreographed trajectory that borrows velocity from the gravity of other planets along the way. These gravity-assist trajectories, sometimes called slingshot paths, work by flying close to a massive planet and using its gravitational pull to redirect and accelerate the spacecraft. Voyager 2 used this technique very effectively, gaining speed at each planet it visited. For a future Neptune mission, a gravity assist from Jupiter offers the most useful boost, and could reduce transit time considerably compared to a direct trajectory. But Jupiter assist launch windows open only during specific periods determined by the alignment of the planets, and missing one means waiting years for the next. Planetary scientists and mission planners track these windows carefully, aware that a decision delayed is often an opportunity lost for many years. Once a spacecraft reached Neptune and entered orbit, it would face a second challenge: communication. The speed of light is the universal limit, and at 4.5 billion kilometers, even light takes roughly 4 hours and 15 minutes to complete the one-way journey. A signal sent from Earth to a spacecraft orbiting Neptune takes that long to arrive. A response takes another 4 hours and 15 minutes to return. This means that mission controllers on Earth cannot react in real time to anything the spacecraft encounters. If something goes wrong, if a thruster misfires, or an instrument develops a fault, or the spacecraft detects something unexpected in its environment, the response from Earth will not arrive for over 8 hours. This places enormous importance on the spacecraft's ability to manage itself. Modern spacecraft are considerably more capable of autonomous decision-making than the Voyager probes were, and a Neptune mission would be designed from the beginning with this kind of onboard intelligence in mind. But it also means that mission planning must be extraordinarily careful and thorough. There is very little room for improvisation at that distance. Power is perhaps the most practically limiting challenge Neptune is so far from the Sun that solar energy is entirely impractical, as a power source, the sunlight available there, is roughly 900 times dimmer than what reaches Earth, and the solar panels that power spacecraft closer to the Sun would need to be enormous beyond any reasonable design to generate useful electricity at Neptune. The only viable alternative for a mission at this distance is nuclear power. Specifically, what is needed are radioisotope thermoelectric generators devices that convert the heat produced by the natural radioactive decay of plutonium-238 into electricity. These are the same systems that have powered Voyager 1 and 2, the New Horizons mission to Pluto, and the Cassini spacecraft at Saturn. They are reliable, they require no sunlight, and they continue generating power for decades. The New Horizons spacecraft, launched in 2006, is still receiving power from its radioisotope generator and transmitting data from beyond the Kuiper belt. The challenge is that plutonium-238 is not naturally occurring in usable quantities. It must be produced in nuclear reactors, and for much of the late 20th and early 21st century, production had largely halted. The United States resumed limited production, but the available supply of mission-ready plutonium-238 remains constrained, ensuring there is enough of it to support the power needs of an ambitious multi-year Neptune orbiter has been an ongoing concern in mission planning discussions. A probe released from the orbiter into Neptune's atmosphere would add enormously to the mission's scientific return, and would probably be a core part of any design. As we explored earlier in our journey through Neptune's interior, even a descent lasting only a few minutes before pressure overwhelmed the spacecraft would yield measurements of extraordinary value. The elemental composition of Neptune's atmosphere, the precise ratios of hydrogen, helium, methane, ammonia, and other compounds at various depths would tell scientists things about where Neptune formed in the early solar system and how it has evolved over billions of years. The temperature and pressure profile at different altitudes would constrain the interior models. The presence or absence of certain compounds would inform predictions about the diamond rain hypothesis and about the chemistry of Superionic water deeper down. The Galileo probe, which entered Jupiter's atmosphere in December 1995, provides a useful precedent. It descended for about an hour before heat and pressure destroyed it, transmitting data the entire time. That single hour of atmospheric measurements from inside Jupiter fundamentally changed our understanding of the gas giant's composition and dynamics. A Neptune probe would almost certainly do the same, and given how much longer Neptune has been waiting, and how much stranger its interior is expected to be, the results might be even more transformative. A mission of this kind, if given the approval and funding it would need, might launch sometime in the early to mid-2030s. With a Jupiter gravity assist, it could reach Neptune in the late 2030s or the early 2040s. Scientists who are early in their careers today, who have grown up reading about Voyager 2's brief encounter, might spend their most productive professional years working with data from a spacecraft actually in orbit around Neptune. That possibility, still hypothetical, still waiting on decisions not yet made, is, in its quiet way, one of the more hopeful things in planetary science right now. The universe has been patient with Neptune. Perhaps we are becoming patient enough to meet it properly. There is something worth exploring more carefully when we think about mission design, which is what exactly such a spacecraft would be looking for once it arrived. What are the specific open questions that a Neptune orbiter and probe would be positioned to answer? Because the list is long, and understanding it helps illuminate just how much remains genuinely unknown about this planet. The first and perhaps most immediate question is the composition of Neptune's atmosphere. We know the broad outlines: hydrogen, helium, methane, but we do not know the precise ratios, particularly for heavier elements. The ratio of elements like carbon, nitrogen, oxygen, and sulfur relative to hydrogen tells planetary scientists about the conditions under which Neptune formed and the region of the early solar system where it acquired its material. Jupiter and Saturn, being closer to the Sun and formed earlier, likely incorporated different proportions of these elements than Neptune did. Measuring Neptune's atmospheric composition precisely would give us a kind of chemical fingerprint of the outer solar system's formation environment information we simply cannot get any other way. The second major question is the source of Neptune's excess heat. We know Neptune radiates 2.6 times more energy than it receives from the Sun. The source of that internal energy is not fully understood. It may be residual heat from formation, slowly leaking outward over billions of years. It may be related to the sinking of denser material toward the core, a kind of internal differentiation that releases gravitational energy as it proceeds. It may involve processes related to the Superionic water layers and how they conduct heat. An orbiter equipped with instruments to map the planet's thermal emission with precision and a probe that could measure temperature at various depths would go a long way toward resolving this. The third major question is the detailed structure of Neptune's magnetic field. We have a rough picture from Voyager 2, but that picture was assembled from measurements taken during a single, hours-long pass. A true understanding of the magnetic field, how it varies over time, how it couples to the ionosphere and the solar wind, whether it shows regular patterns of change tied to the planet's rotation, requires years of observation, not hours. The structure of the magnetic field is also a window into the interior, because the field is generated by moving conductive material deep inside the planet. A better map of the field is, in some sense, a rough map of the interior. The fourth major question involves Triton. We know Triton is geologically active and covered in nitrogen geysers. We know its orbit is retrograde and slowly decaying. We know its surface is young enough that it has been reshaped relatively recently in geological terms. But we have seen it from only one approach trajectory at one particular geometry on one particular day. An orbiter carrying cameras, spectrometers, and other remote sensing instruments would be able to map the entirety of Triton's surface in detail, watch its geysers over an extended period, and measure its thin atmosphere as it changes with the seasons. Given that Triton is likely a captured Kuiper Belt object, a world that formed in the cold outer reaches of the solar system and was then pulled into Neptune's grip, understanding it in detail would also tell us something about the Kuiper Belt itself and the nature of the small icy worlds that populate it. The fifth question is about the ring arcs. The clumpy, asymmetric structure of Neptune's rings is theoretically unstable over long timescales. Something must be maintaining the concentrations of material we call arcs. Whether that something is orbital resonances with nearby moonlets or something else, we cannot be certain from the available data. A long-duration orbiter could observe the ring system continuously, tracking whether the arcs are changing, whether the material within them is being replenished from some source, and whether the moons thought to shepherd them are actually playing that role. Each of these questions, taken on its own, would justify a visit. Together, they make the case for a sustained, dedicated presence at Neptune that is, scientifically speaking, almost impossible to argue against. Before we leave the question of future exploration, there is one more dimension worth thinking about, and that is what Neptune exploration would mean not just scientifically, but for the people involved in it. Outer solar system missions operate on timescales that span careers. The scientists who proposed and designed the Cassini mission to Saturn spent years on its development before launch, then managed it through 13 years of orbital operations, and many of them had worked on it for more than 2 decades by the time it concluded in 2017. The engineers who built the Voyager probes in the mid-1970s were, in many cases, young professionals just beginning their careers. By the time Voyager 2 reached Neptune in 1989, those same engineers were in their 40s and 50s, watching the culmination of work they had begun as younger people. There is something genuinely moving about this. Science at its largest scales is a multi-generational enterprise. The people who design a Neptune orbiter today may not be the people who are still active in the field when it arrives. Careers end. Retirements come. And yet the work continues past from one generation of scientists to the next, each one adding their piece to a structure that will outlast any individual contribution. For many of the planetary scientists who study Neptune today, a dedicated mission is something they hope to see in their professional lifetimes. They have spent careers extracting every possible piece of information from 35-year-old Voyager data, supplementing it with careful telescope observations, building and refining theoretical models, and waiting. They know, better than anyone, how much more there is to learn. And they know, better than anyone, how much is riding on someone deciding that the journey is worth making. If that decision is made, if a mission is eventually funded and launched and sent toward the edge of the solar system, then the scientists who receive its data will be, in some sense, the inheritors of a long patience. They will open files containing measurements from inside Neptune's atmosphere, or detailed maps of Triton's surface, or a precise accounting of how the magnetic field has evolved over years of observation, and they will be the first human minds to hold that knowledge. That is a remarkable thing to think about. Somewhere out there is information about Neptune that no mind has ever touched, waiting in the physics of the planet itself, ready to be measured when we finally send something capable of measuring it. The universe keeps its records patiently. We just have to go and read them. There is a question that sometimes comes up when people learn about Neptune, about how extreme it is, how hostile, how remote. And the question is essentially, could anything live there? It is a natural thing to wonder. We are a species that looks at every new environment and asks whether something might call it home. We have found life in deep ocean vents where sunlight never reaches, sustained entirely by the chemical energy of minerals reacting with water. We have found life in the acidic hot springs of Yellowstone, in the dry valleys of Antarctica, in clouds of sulfuric acid high in Venus's atmosphere. In the upper reaches of Earth's own atmosphere, viable bacterial spores float in the stratosphere. Life on Earth is remarkably tenacious, and it has a way of confounding our assumptions about where it cannot exist. Neptune, however, presents challenges that go considerably further than any extreme environment we have found life surviving on Earth. Consider the winds first. 2,000 kilometers per hour, sustained across the entire upper atmosphere. Any chemistry that began to organize itself, any complex molecule that started behaving in an interesting way, would be dispersed almost immediately by those winds. Chemistry needs time to build on itself. Life, as far as we understand it, requires an environment where concentrations of interesting molecules can accumulate and interact over extended periods. Neptune's upper atmosphere offers no such stability. Consider the temperatures. In the upper cloud layers, the temperature sits around -210 degrees Celsius. At those temperatures, most of the chemical reactions we associate with biology would proceed at essentially zero speed. The reaction rates that biology depends on slow exponentially as temperature decreases, and at Neptune's cloud-top temperatures they would be so sluggish as to be effectively halted. Consider the pressure gradient. As you descend into Neptune, temperature rises dramatically and pressure climbs into ranges that would destroy any structure we know of that life uses to organize itself: cell membranes, proteins, nucleic acids. The conditions that might be warm enough for some chemistry to proceed are simultaneously so pressurized that the materials needed for that chemistry would be in exotic states quite unlike anything biology has ever been shown to manage. And yet, there is a region in Neptune's atmosphere at depths below the visible cloud tops, but above the crushing pressures of the interior, where temperature and pressure conditions overlap, at least in principle, with conditions that exist in some extreme environments on Earth. This region, sometimes called the temperate zone in discussions of giant planet atmospheres, may contain liquid water at certain altitudes, or at least water in a liquid-like state. The chemistry available there, hydrogen, carbon, nitrogen, oxygen, all present in the atmosphere, is broadly the same set of atoms that life uses on Earth. This does not mean life exists there. There is not a scrap of evidence that it does. But the habit of assuming life cannot exist somewhere, and then discovering it does, has happened often enough in the history of biology that dismissing the question entirely feels premature. The more measured way to think about it is this: we do not understand life well enough to rule out any environment with complete confidence. We understand life only as it exists on Earth in a single continuous lineage that traces back roughly 4 billion years to a common ancestor. Every observation of life is an observation of variations on one theme. We do not know whether that theme is the only possible one, or merely the one that happened here. Neptune is, in human terms, entirely uninhabited and, as far as we can determine, entirely uninhabitable. But it is a place worth wondering about, gently, in the way that the dark inspires the imagination without demanding certainty from it. Let us take a moment to think about what Neptune means in the context of the entire galaxy, not just our own solar system. Because this is, quietly, one of the more important perspectives we can bring to our understanding of this overlooked blue world. When astronomers study other planetary systems, the systems around other stars, which we have been detecting and cataloguing in increasing numbers since the 1990s, they find that our own solar system is, in certain respects, not typical. The giant gas planets of our system, Jupiter and Saturn, are in some ways unusual. The 4 rocky inner planets are in some ways unusual. The arrangement of our solar system, with small rocky worlds close in and large planets further out, is one pattern among many rather than the universal standard. What is not unusual, and what in fact appears to be the most common pattern, is planets of intermediate size. Planets larger than Earth but smaller than Neptune. Planets in the rough size range of Neptune and Uranus themselves. These objects, sometimes called sub-Neptunes or mini-Neptunes, depending on where they fall in the size distribution, appear around a very high fraction of stars that astronomers have studied. They are, by any reasonable measure, the most common planet type in the observable galaxy. This matters enormously. If we want to understand what most planets are like, if we want to understand the conditions on the majority of worlds in the universe, then understanding ice giants is not a niche interest. It is perhaps the most central thing planetary science could pursue. The interior structure of a mini-Neptune around a distant star is something we will never be able to probe directly. We will never send a spacecraft there. We will never drop a probe into its atmosphere. We will study it from the light it blocks as it passes in front of its star, and from the tiny gravitational tug it exerts on its host, and from the way its atmosphere might absorb certain wavelengths of starlight. These are powerful techniques, but they are indirect, and they depend on models, on theoretical frameworks that tell us how to interpret what we observe. Those models are built, in part, from what we know about Neptune and Uranus. The Superionic water we believe exists inside Neptune informs predictions about the interior structure of sub-Neptunes everywhere. The magnetic field behavior we observe at Neptune contributes to theories about how magnetic fields can form in water-rich planetary interiors. The atmospheric chemistry we have measured, however incompletely, at Neptune shapes our expectations for what similar planets around other stars might contain. Every piece of knowledge we gather about Neptune is, in this sense, multiplied across a galaxy full of similar worlds, improving our understanding of one nearby visitable example, imperfect and incomplete as that understanding still is, echoes outward across the billions of planets we will never directly touch. Neptune is not just itself. It is a representative of the most common kind of world in the universe, sitting close enough for us to study in ways no other example allows. That is a scientific opportunity that, once fully recognized, becomes quite difficult to set aside. Let us come back to what might be the most fundamental mystery Neptune presents, and sit with it for a while. Neptune has winds exceeding 2,000 kilometers per hour. It generates 2.6 times more heat than it receives from the sun. It has storms that appear and vanish without explanation. It has a magnetic field tilted almost 50 degrees from its axis and displaced from its center. Its interior contains diamond rain and Superionic water. Its largest moon is captured and slowly spiraling to its end. Every one of these things, taken individually, would be a fascinating footnote about an unusual planet. Taken together, they paint a picture of a world that is, in some deep sense, not like anything we have modelled or understood completely. Neptune breaks, or bends, or complicates almost every simple framework we try to apply to it. And the most humbling part of this is not that Neptune is so strange. It is that we have known Neptune was this strange since 1989, and in all the decades since, we have not sent anything back to look more closely. We know that the winds are fast, but we do not know precisely what drives them. We know the magnetic field is tilted and offset, but the detailed mechanics of why are not fully understood. We know the planet produces excess heat, but we do not know why Uranus does not. We know diamonds may form and fall inside it, but we have never measured this directly. We know Triton is captured and geologically active and covered in geysers, but we have only seen it from one vantage point on one day more than 30 years ago. Neptune is a planet that has been raising its hand quietly, persistently, for decades. It has more questions than almost any other object in the solar system, and the answers to those questions have implications not just for Neptune itself, but for the billions of worlds across the galaxy that may resemble it. There is something worth sitting with in this particular combination of facts. We know Neptune is strange. We know why it matters. We know what we would need to do to understand it better. And we have not yet done it. This is not a criticism of anyone. The science community that studies Neptune cares deeply about it, and the constraints of budget and priority and feasibility are real. But it is a recognition that some of the most important questions in planetary science are also some of the most patiently waiting ones. In some ways, this is the nature of science at the frontier. Progress is not linear. It comes in steps, each one requiring resources that must be assembled, arguments that must be made, technology that must be built and tested. The knowledge we want is on the other side of an enormous logistical challenge, and that challenge is real, even as the questions remain open. What is quietly hopeful about the present moment is that the conversation around Neptune is more active than it has been in a long time. The 2022 Decadal Survey, the community's formal prioritization document, placed ice giant exploration prominently among the goals of the coming decades. While the immediate focus was a Uranus orbiter and probe, the scientific principles that make Uranus compelling apply equally to Neptune. The momentum, in other words, is pointing outward. Toward the cold blue edge, the sun, as seen from Neptune, is not the blazing disk of light that fills our sky on a clear morning. At 4.5 billion kilometers of distance, the sun shrinks to a very bright star, far brighter than any other star in Neptune's sky, but not the overwhelming presence it is from Earth. You could look at it with more comfort from Neptune than from here, though the cold around you would be something beyond any cold we experience in ordinary life. The sky from Neptune, if you could somehow float above its cloud tops and look outward, would be dark, even by the standards of the outer solar system. Not as dark as truly interstellar space, but dark enough. The stars would be bright and still, the way stars look when there is no atmosphere to scatter their light. The Milky Way would be present, its soft band of stars arching across the darkness. Below you, the clouds would be that deep blue, vivid and rich, even in the dim light. Winds would be screaming horizontally at speeds that would tear any structure apart. But from above, looking down, it would simply look like a texture of cloud patterns, shifting and reorganizing. A dark spot might be visible somewhere in the southern hemisphere, or perhaps not, depending on the year. The storms come and go. Triton would be visible as a tiny icy crescent, orbiting backward, its nitrogen geysers invisible at this distance. The thin arcs of the rings would be barely detectable except at the right angle. The other moons would be too small and too dim to see easily. It would be, in its quiet way, beautiful, cold and remote and utterly alien, but beautiful. And there is something else worth imagining as you float above those blue clouds. Somewhere in the night sky above you, among the thousands of stars visible to the eye, is the sun a bright point, steadier than the others, unmistakably the brightest thing visible, but still just a point. And orbiting that point, at various distances, are 7 other planets, including one small blue-green world, the third from the sun, where at this moment someone might be looking back outward with a telescope, trying to make out the details of the clouds below you. We are connected to this place, even at this distance. It is part of the same gravitational family we call home. And that is perhaps the thought to carry, that even at 4.5 billion kilometers, Neptune is not foreign. It is ours. Part of the same story, the same neighborhood, the same long ongoing process of a solar system trying to understand itself through the eyes of one of its smaller inhabitants. We are nearing the end of our time with Neptune tonight, and there is one more thing worth sitting with before we close. For most of human history, Neptune did not exist, not in any meaningful sense. People lived and died and built cities and wrote poetry without knowing it was there. The ancient astronomers catalogued the visible planets Mercury, Venus, Mars, Jupiter, Saturn, and the idea that there might be more further out beyond the reach of the naked eye was not something they had reason to consider. Those ancient observers were not wrong. They catalogued what could be seen, applied careful logic to what they observed, and built models of the cosmos that held together remarkably well for centuries. The limits of their knowledge were the limits of their tools, and within those limits they did extraordinary work. Neptune was not discovered until 1846. And the discovery itself was one of the great intellectual achievements in the history of science, not because someone looked through a telescope and happened to see it, but because mathematicians predicted it existed before it was seen. In the early 19th century, astronomers noticed that Uranus was not behaving quite the way their models said it should. Its orbit was slightly off-nudged in ways that could not be explained by the known planets. 2 mathematicians, working independently and using the same observed irregularities, calculated where an unknown planet would have to be in order to produce those nudges. One was Urbain Le Verrier in France. The other was John Couch Adams in England. The story of their parallel work is itself a fascinating episode in the history of science. 2 people on opposite sides of the English Channel, without knowledge of each other's efforts, arriving at essentially the same answer through the same mathematics. Adams completed his calculations first, but had difficulty getting the British astronomical establishment to take them seriously and act on them promptly. Leverrier, working a few months later, sent his calculations to the Berlin Observatory, where they were received by an astronomer named Johann Gottfried Galle, who was willing to look immediately. On the night of September 23rd, 1846, Galle pointed his telescope at the part of the sky Leverrier's math predicted and found Neptune within a degree of where the equations said it would be. A planet discovered by mathematics, found not by sight but by logic, by the patient application of physical law to tiny discrepancies in data. It was one of the first demonstrations, clear, dramatic, and essentially undeniable, that the universe is lawful enough, orderly enough, that you can find things in it without looking, simply by reasoning carefully from what you already know. This moment has a particular resonance that is worth letting settle. We are creatures who can sit on one small world and, by measuring the tiny wobble in another world's path, infer the existence of something we have never seen, calculate where it must be, and then look there and find it. That is not a trivial capability. It is one of the most remarkable things minds have ever done. Neptune existed long before anyone knew it was there. It had been tracing its slow orbit for 4.5 billion years before a French mathematician wrote down an equation that pointed at it. The universe does not wait for us to notice it. But when we do notice, when we pay close enough attention and reason carefully enough, it turns out to be knowable. That is, in a deep and quiet way, one of the most comforting facts there is. There is something comforting about that, in a way that goes beyond the specific case of Neptune. The universe rewards careful attention. It doesn't hide things arbitrarily. If you pay close enough attention to what you can see, it will sometimes tell you what you cannot. And that principle, the principle that the cosmos is comprehensible, that it yields to patient and careful inquiry, is perhaps the most valuable thing that the history of science has demonstrated. Neptune is one of its clearest examples. Neptune has been waiting. It will keep waiting. Somewhere out there, right now, the winds are blowing. 2,000 kilometers per hour, horizontal, unceasing, faster than the sound of any thunder on Earth, faster than a bullet, faster than anything our atmosphere has ever managed in its most violent moments. Those winds are blowing right now, as you read these words, in the cold blue upper atmosphere of a world that most people will never think about. A dark storm is perhaps forming in the southern hemisphere, drawing material upward from the depths, organizing itself into a rotating vortex the size of a continent. Or perhaps one is dissolving, losing its structure, its winds merging back into the general chaos of the atmosphere, its identity disappearing as though it had never existed. Neptune makes no promises about its storms. They come when they come, and they go the same way. In the interior, if the physics is what we think it is, diamonds are falling through hot, dark, immense pressure, slowly accumulating wherever they settle, building up over geological timescales into a layer of crystalline carbon that no eye has ever seen, and perhaps none ever will. Superionic water is pressing against itself, conducting electricity in that strange crystalline but fluid state that has no name in ordinary language, participating in the generation of a magnetic field that wobbles and tilts as the planet spins a field that, even as you rest here, is sweeping through space in its peculiar offset pattern. Triton is orbiting backward, precisely and patiently, its trajectory carrying it slowly, incrementally, almost imperceptibly inward with each passing year. Its nitrogen geysers are briefly lifting dark plumes into a thin atmosphere before the wind catches them and carries them downward in streaks across the ice. Something is happening on that moon right now, some slight geological settling, some small eruption of nitrogen gas, some incremental change in a surface that has been frozen for billions of years and will be frozen for billions more. And we, from our small warm planet inside the frost line, look outward and wonder. Neptune is not the planet that asks to be noticed. It does not have Saturn's obvious rings, or Jupiter's famous storm, or Mars's obvious rust-red face. It sits at the edge of the neighborhood, quiet and extreme and strange, doing things we don't fully understand in a place we've barely visited, in a cold blue light that barely reaches it from a sun that looks like nothing more than a very bright star from its vantage point. And perhaps that is why it is worth knowing about. The things we overlook are so often the things with the most to teach us. The questions we haven't answered are almost always more interesting than the ones we have. And the worlds at the edges, the ones that don't fit neatly into our frameworks, the ones that behave in ways our models don't quite account for those, are the ones that have something genuinely new to say. Neptune has something genuinely new to say. We just haven't gone back to listen yet. Tonight you have travelled 4.5 billion kilometres without leaving where you are. You have passed through cloud tops of methane ice into winds that move faster than anything our atmosphere has ever produced, and descended through layers that transition from gas to dense fluid to something our language doesn't have a clean word for. You have visited the interior where diamonds might fall through darkness and where water behaves as both a crystal and a conductor, where the distinction between solid and liquid loses its usual meaning. You have encountered a magnetic field that breaks the rules we once thought were universal, tilted and offset and wobbling as the planet spins. You have circled a moon that orbits backward, its days numbered on a 3.5 billion year clock that has been ticking since before the Earth's continents took their current shapes. You have spent time with a planet that has been visited exactly once, by a spacecraft that launched before many of the scientists who study it were born, carrying a golden record of sounds from a civilization that was still learning what the outer solar system looked like. Neptune is the most overlooked world in our solar system, and it may be the most quietly astonishing. The questions it holds are not small questions. They are questions about how planets form and evolve, about what drives weather on a world with almost no sunlight, about what states matter can occupy under conditions we can barely replicate in a laboratory, about what the most common type of planet in the galaxy is actually like from the inside. These are questions that matter not just for understanding Neptune, but for understanding the universe we live in. And now, having spent this time with it, you can drift. There is nothing left to do tonight but rest. Let the winds of Neptune blow without you. Let the storms form and dissolve on their own mysterious schedule. Let the diamonds fall, if they are falling, in their slow and ancient descent through the dark interior of a planet that has been patient for 4.5 billion years and will be patient for 4.5 billion more. The universe is very large, it is very old, and it is very patient. And somewhere out there, moving through interstellar space with a golden record and the sounds of Earth whale song, wind, a Bach partita, greetings in 55 languages, the laughter of a child Voyager 2 continues its journey into the dark between stars. It passed Neptune once, more than 30 years ago, and kept going. It carries with it a small piece of what we were at that moment, curious, reaching outward, willing to spend 12 years crossing empty space for a single day of data near a planet we barely understood. That impulse to look outward, to build something and send it, to close the distance between ourselves and the unknown, even when the unknown is 4.5 billion kilometers away and the journey takes 12 years, that impulse is one of the genuinely beautiful things about being the kind of creature we are. Let that be the last thought you carry tonight. Not urgency. Not the complexity of magnetic fields or superionic water or retrograde moons. Just the simple, warm, quietly remarkable fact that we looked outward, we built something, and we sent it. Into the dark, toward Neptune and beyond. The universe has more to show us. There is time. Sleep well.